Very good. So we saw yesterday how to compute the weights of the neural networks using gradient descent. And what we will see now is an extension of the gradient descent with some concepts that we already know. One of them is the stochasticity. That is, we will not take all the elements that all the observations that we have for our data set, but we will take only subsets of them. And here you cannot see because it is a PDF, but it was moving. Actually, the link has disappeared already. But I have found this one. This one, in which you see that the different techniques, stochastic gradient descent, they make kind of zigzagging while approaching the minimum. And here you have with momentum, RMS probe, Adam, so you have different versions of them. So the difference is in the trajectory and how many iterations they need to convert to the global minimum or to the local minimum. Yeah. So what we will see is these differences, how these different algorithms optimize the weights of the neural network. So these are the theta and the weights of the neural network. And then the loss function depends on theta. And then stochastic gradient descent is just updating the weights with a learning rate. Here is represented with epsilon, with the gradient of the loss function. And this gradient is computed in a small subset of the observations. So typically the batches have size of 8 points, 16 points, up to maybe 1,000 points. But typically a small numbers like 8, 16, 32, they are more common. And then you have a stochastic gradient descent with impulse or with momentum. So here the idea is similar. So, but now we will have a kind of velocity. So the weights will be updated with the velocity, and the gradient updates the velocity. So it is this thing that you are moving in some direction, and then even if the gradient is flat, because you have an impulse, you have a momentum that is given by this velocity. This rho is a number typically 0.9, 0.95, something like that. So you will take a few iterations to go from a given velocity to 0, because it will decay very slowly. And here again, if you go to this web page, you can play with the momentum parameter and with the learning rate, and you would see how the trajectories look like. So, for instance, here you see that at the beginning you have a lot of zigzagging, and the movements are not very effective, but at some point you get a better momentum, and then you go more smoothly to the optimum. So this is the stochastic gradient descent with momentum. This is a refinement of that. So here, what you can look at this as a gradient descent. So if you look at this part of the numerator is gradient descent. And the difference is how the learning rate is updated. So the learning rate here, you see is divided by the square root of the gradient at t plus 1. So what is this? This is actually not the gradient, but the norm of the gradient. So the norm of the gradient is at 0, and then for every iteration, you compute what is the gradient of the loss function with respect to the weights. You compute the norm of that. So that is maybe the notation is not the best. It would be better to put double bars.
to put the norm, but you compute the norm, and then you keep accumulating the norms. And then this is the square root of the norm and some small constant to avoid dividing by 0. So the learning rate is somehow adaptive to the history of the grading norms. And that is a problem with this. This is called ADAGRAD, and ADAGRAD was also some advancement in these stochastic optimization algorithms. But the problem with ADAGRAD is that if the training takes too long, then this GT will grow because you are adding all the time positive numbers. So this is a non-monotonic signal or variable that grows with time, and then the learning rate decreases with time monotonically again. So at some point, if the training is too long, you're learning very little because you're divided by too much. So the next iteration to that is this RMS probe. So here we have the previous algorithm. So now with this RMS probe, what you're trying is to forget what was the very long history of these cumulative gradient norms. So here you have you update your gradient norms with alpha plus 1 minus alpha, the current gradient norm. So let's say that alpha is 0.9. So this 0.9 will make the gradient norm to decay with time, and then you are updating with the current gradient norm. So this is again a very well known algorithm, very much used, and the intuition is the same. So it is gradient descent with a learning rate that depends on the gradient norm. And now you can see how it acts. So let's say that the gradient here, or the recent history of the gradient, has a very large norm. If it has a very large norm, that means that the function is changing a lot. So if the function is changing a lot, it is better to give small steps because you don't know, otherwise you would be zigzagging probably. If the gradient is very smooth, so it is not as smooth, but it is very flat, so it is very close to 0, then if it is close to 0, it is better to make big jumps. So if the gradient norm is close to 0, then you are dividing by a small number and the learning rate is higher. So in flat regions, you're making big, long steps, and in the very sharp regions, you're making very small steps. And then you have Adam. Adam is a mixture of the two. So you will have momentum, and you will have this velocity update of RMS probe. So it is just so the momentum goes with the gradient, the velocity goes with the gradient, with the norm of the gradient or the square of the gradient. But the idea is the same. So you have a momentum that is somehow this beta 1 minus beta 1 is the trick to make local histories, the same for the velocity. And then the update is just the standard one. The standard of these adaptive algorithms. And here you have more variants of that. So, and all of them result into different trajectories, as we saw here. So it is how fast and how many iterations it takes to go to the local minimum. And if you want to explore them, you can, for instance, this is a notebook in which they explore all these different optimizers. And then, particularly with neural networks, when you use these libraries, for instance, here I'm showing the code for TensorFlow. So in TensorFlow, the gradient that are the difficult part. So they are somehow automatically calculated. So, and the trick is this thing in which you do TensorFlow gradient time, and then you say which variables you want to track. And then the gradient tape will look into how these variables are used in your code. And then, so for instance, here we have set as a function of x and y. And then, because this was under the gradient tape, you can compute derivatives. So you can say derivative of set with respect to x, with respect to y, and it is the gradient tape that is calculating these gradients with respect to the variables that you want. But, and here you have kind of similar code. So it is this has been a great advance because otherwise it would be impossible to train these complicated neural networks if you had to compute the derivative as we did yesterday. Okay, it was quite mechanic, but you saw it was quite a nightmare even for a very small network. So you don't have to compute by hand. So it is these libraries that keep track of the gradients. And this has been really a great advance. And then, the same idea that all these variants, what they change is how they convert the global minimum. So let's say that the global minimum, what it is here, and then you start here, and then the different algorithms, for instance, this one with momentum, you see, okay, it is a nice idea, but it is not the best. Somehow it goes too far away. And these ones, RMS probe or even a stochastic gradient descent is doing a better job. But for instance, momentum things are very good when the gradient becomes very flat. When the gradient goes to zero, then you need momentum because otherwise you cannot escape that idea. And also something that is very common in neural networks is how to organize or how to schedule the learning rate. So in principle, the learning rate should be large, or relatively large at the beginning, so that you can start looking for a minimum. But as you get closer and closer to the minimum, then you don't want to move too far. So the learning rate should be decreased. This is one scheduling. And here you may have a preconceived idea. I will do 4 iterations at one learning rate. Then I will decrease by gamma. Then I do 4 iterations at the new learning rate. I decrease by gamma, and so on. There is a problem with this. That is that it may get trapped very easily to a local minimum. So these schedules in which the idea is you decrease the learning rate, but at some point you increase it again and you make it big again, so that you allow the algorithm to escape from the local minimum, and then you decrease, and then you increase again. So if you are in a very good minimum, it doesn't matter if you increase the learning rate, because even if you make a big jump, you will come back to the global minimum. Maybe this scheduling is too extreme, in which the learning rate somehow may make you big jumps that you have to undo at some point. But then this scheduling somehow in which there is an envelope that makes the learning rate to go to a small number. This is good, but it keeps this idea of regularly increasing the learning rate just to allow for escaping from the local minimum. Any question? Neural networks? No. Okay, so then we go to the very last lecture, which is a very short lecture on some problems. Actually, I cannot think of any data analysis problem in which it doesn't start with minimize something or maximize something. If you know any problem that doesn't involve minimization or maximization, just tell me, because I cannot think of anyone. So everything is an optimization problem, and you have to find the best way to solve it, and best means optimizing. Okay, so let's see some problems. And one of these is this recommendation problem. So the recommendation problem is you have a number of people, let's say that you have a number of movies, for instance, and then there is a scoring of these people to the some of these movies. So there is a full matrix, but this matrix has some empty cells. So there are cells for which you have not measured. And then you want to complete the matrix. This is this problem matrix completion. And then what you do is to factorize the matrix into the product of two sub-matrices or two smaller matrices. And somehow the first matrix will characterize the people. So it will put people, so people with similar roles will be similar to each other. And the same for the movies. So there is now a column for each one of the movies. And when you multiply the two, what you have is the full matrix. So what you want is to find two matrices such that the multiplication of the two is consistent with your observations. And the places where you didn't observe data will be automatically filled by this multiplication. Okay, so let's formulate that. So what we have to say is that I want to, this is my complete matrix R. R will be U transpose V. And then what I have to is, okay, U transpose V is for the element IJ is UI, so it is the column or the row, this is U transpose, it is the row I times the column J. So this multiplication has to be similar to my observations for the set of observations I have, and similar in a least square sense. And then there is some regularization. So I don't want these matrices to have very large values because probably that is doing overfitting. And then there is somehow these U and V's, they are also called, so the columns and rows of these matrices, they are called the latent space. So the latent space, there is a latent space of people, and there is a latent space of movies. And what we hope is that these vectors, so similar people go to similar vectors. So the regions in the latent space somehow represent well the people, and in the latent space of movies, similar movies, they are also close together. And we have expressed this with movies and people, but this matrix completion problem appears in many other contexts. Another problem that now you would be able to solve would be this resource allocation in the data center. So you have a data center with many computing nodes, and in these computing nodes you receive a lot of tasks, and these tasks will request some resources. So they will request some CPU, some memory. Each one of the nodes, they have a limited capacity, so they have a number of CPUs and a maximum amount of memory. And then the goal is how to distribute this incoming stream of tasks into the different nodes, such that there is something that is maximum. So it can be minimum cost or maximum balancing load, so that all the nodes are equally loaded, or minimum energy consumption, or minimum amount of time in execution or medium waiting time in queues or whatever. So how to formulate this problem? So let's say that you have a number of tasks, a number of servers, you have the resources demanded by each one of the tasks, the resource capacities by each one of the servers, and some cost of assigning the task I to the server J. And for instance, this cost can be energy assumption, delay in execution, or whatever. And then your variables will be 0, 1. That is 1 if the task I is assigned to the server J. So what you want is to minimize the cost subject to some constraints. And these constraints are that each task is assigned exactly once. So you value like this way. That they don't exceed the capacity of each one of the servers. So for each one of the servers, the resources requested by each one of these tasks, the sum of these resources is smaller than the capacity, and that these variables are binary, so they are 0 or 1. And this can be even more complicated because somehow we have presented this static version, but now this would be dynamic, in which the capacities are somehow changing because there are already some tasks running, and there are new tasks coming. So you don't know how the task will behave in the future and what will be the request. So the dynamic version of this problem is even more complicated. A different context. So, for instance, in marketing. So let's say that you are in a company that have a list of customers. Each one somehow has some profile that is characterized by demographics. So demographic is age, education, whatever, the browsing history, the purchasing data. And for each of the customers, you have multiple marketing actions. And for instance, you could send an email, offer a discount, a personalized recommendation. Here you have many different marketing actions. Each one of these actions has a cost. They have a conversion probability, so the probability that the person is really influenced by this action and buys something. And there is a potential reward. So the goal is to maximize the expected return of the campaign and constrained by budget and possibly fairness, that is not ignoring some customer segments. So how to formulate that? So you have a number of customers, you have the different actions that you can do for the customer I. Then you have this XIA, that is a binary variable, that is the action A is selected for customer I and otherwise the city. And then the probability of conversion if action A is applied to customer I. So this is a given, this is what you can control, so what you can have to optimize. The expected reward, again, this is a data, so something that you need. Cost of applying action to customer I, and the total campaign budget. So what you want is to maximize the reward. So it is, I take this action, and then by taking this action on this customer, I will have some reward with some probability, and I have to sum over all customers and all actions. And then there are some constraints. That is one action per customer. So at most one action per customer. So this the sum over all the actions for a given customer has to be smaller or equal 1. The total budget constraints, so the cost associated to all my actions has to be smaller than the given amount, and then these binary constraints. And another one is, this is a different problem. So this one appears in experiment design. So experiment design is, I have to take some measurements to make a regression. before taking the measurements, how do I plan my measurements? So this is a whole field in mathematics and in statistics, this experimental design. Okay, so once I do the observations, I will do this linear regression, for instance. So Y will be my responses, X will be my predictors, and beta are the parameters of the regression. So I want to know beta. So we already know what is the least square solution of this problem. So the least square solution is this one. Well, you already know it. And what you may not know is, okay, because the observations are random, the beta will also be a random variable because the observations are random. So if this is random, then what is the covariance of beta? So the covariance of beta somehow gives you an idea of how variable your beta is. And the covariance of beta, this is a result from statistics. It is this one. So it is the variability of the data times the inverse of the X transpose X matrix. So before doing the experiment, what you control is something related to X transpose X. So somehow, let's say that you make X transpose X large in some sense, and the sense typically is the determinant. So if the determinant is large, then because you are inverting this matrix, you will be dividing by a large number. So this sigma square will be divided by a large number. And then your betas will be less valuable. So what you want is to maximize the determinant of this. This is one possibility. There are many other possibilities, but minimizing or maximizing the determinant of it is a common one. And before doing that, what we will do is we will construct something that is called the weighted information matrix. So let's say that some of the, so you propose some points to measure, and then these points to measure, each one will have a different weight. The weight can be associated to how important that point is for you, or how closely that point is, or whatever. So it may have some weights. The sum of all the weights is add up to 1. And then you construct this weighted information matrix. And then you maximize or you optimize something related to that. So for instance, this the optimal design, what tries to do is for the maximizing the determinant of the information matrix subject to the constraints, that the weights are larger than 0 and they are add up to 1. So everything, I would say almost everything in data analysis involves some optimization problem. So now what we have is a very powerful tool to solve almost any problem. The problem is how to translate that into something I can optimize. And somehow the kind of problems we have been looking in class are kind of toy problems in which I can do it in one morning. But real life problems, they are extremely complicated, but the tools that you use to solve them are exactly the same as these ones. So with this, we finish the course, the theoretical part of the course. Any question about it? No?